Welcome to the lecture on complex numbers. In this lecture we're going to talk about imaginary numbers. You may have heard of the imaginary number I, which represents the square root of -1. And the reason this imaginary number was created or defined is because there's limitations on the real number system. In the real number system, we're not allowed to take the square root of a negative number or even any even root of a negative number. So we can't take, for example, the square root of -4 or the square root of -100. Those are not defined to be real numbers. But if we create this imaginary number I to represent the square root of -1, then we will be able to express these numbers as complex numbers. So for example, if I have the square root of -4, we could split this up into the square root of 4 times the square root of -1, and we know that the square root of 4 turns into a 2, and we're now going to call the square root of -1 I. So square root of -4 becomes the imaginary number or the complex number 2I. If we have the square root of -100, we're going to do exactly the same thing. This becomes the square root of 100 times the square root of -1. Square root of 100 reduces to 10. Square root of -1 becomes I, and so this becomes the complex number 10I. If we have negative square root of -144, remember here that we are not allowed to cancel out these two negatives. One is outside of the radical, one is inside. So first we need to simplify the square root of -144. We can break that up into the square root of 144 times the square root of -1, and the negative that's on the outside will just stay put. So that negative is going to stay there. Square root of 144 turns into a 12, and the square root of -1 becomes our I. So this is the complex number, -12I. In general, complex numbers are going to be any numbers of the form a plus bi, where a and b can be any real numbers. So if b is 0, then we're including all of our real numbers. So every real number is also a complex number. But if b is not 0, then we also will have an imaginary part as well, so parts that have an I next to them. When we talk about complex numbers, some of the things that you're going to have to be able to do with them are your basic operations. So let's start by talking about how you add and subtract complex numbers. When you add and subtract complex numbers, you're going to treat them just as if they were expressions with x's in them, where you want to combine like terms. So for example, -2 plus 6i plus 3 plus 2i. If I want to add, I'm going to need to add the like terms with the like terms. So the number part with the number part, and the I part with the I part. So -2 plus 3 becomes 1, and 6i plus 2i is like 6 apples plus 2 apples. That's going to be 8 apples. So our answer here is just 1 plus 8i. So adding and subtracting complex numbers is just how you would add or subtract like terms. In the next example, we have subtraction. So the one thing you want to be careful about with subtraction is making sure that you distribute your negative across parentheses first before you start combining like terms. This first set of parentheses doesn't have anything out front, so these first parentheses aren't even necessary. I can just go ahead and drop them. But the second set is necessary because I do need to distribute that negative across. So this will become -3 minus 2i. So adding like terms, 9 minus 3 is 6, and I minus 2i becomes -i. So my answer is 6 minus I. Okay, so we talked about how you add and subtract complex numbers. The next thing we're going to talk about is how you multiply them. And before we get to that, we need to talk about the fact that if we know that I is -1, the square root of -1, then look what happens if we were to square both sides. So if I square both sides, then the left side becomes I squared, and the right side becomes the square root of -1 squared. And you know that a square root and a square undo each other. So these would cancel each other out, and that tells us that I squared equals to -1. And that's something that you want to memorize, because we're going to use that to help us simplify expressions. So anytime you come across an I squared, you're going to want to replace it with -1 and simplify from there. So for example, when we multiply complex numbers, we're going to multiply, again, just like we would with variables. 5i times negative 3i, we're going to do the number part times the number part. So 5 times negative 3 would be negative 15. And then the I times the I becomes I squared. But based on what we just talked about, you want to remember that I squared is the same thing as negative 1. So this I squared turns into a negative 1 times the negative 15 that we already had, so the final reduced answer is just 15. So we started with two complex numbers, two imaginary numbers, and we ended up with a real number. On the next example, we're going to do the same thing, but this time we're taking a monomial or single term times two terms, so we just want to make sure that we distribute properly. So we're going to want to take 5i times negative 6. So 5 times negative 6 would be negative 30, and the I stays put. Then we're going to take 5i times 2i. 5 times 2 is 10. I times I becomes I squared. As soon as you see an I squared, you want to replace that with a negative 1 and simplify from there. So 10 times negative 1 becomes minus 10, and this negative 30i out front can just stay put. And here is our simplified answer. In the next example, we have two complex numbers that we want to multiply together, so we're just going to FOIL. We're just going to follow our FOIL process. So first times first would be 7 times 3, and that's 21. Outer times outer would be 7 times I, or positive 7i. Inner times inner is minus 2i times 3, that becomes minus 6i. And last times last is negative 2i times I, which is negative 2i squared. Now remember that I squared immediately turns into a negative 1 times the minus 2 that was out front. So negative 2 times negative 1 becomes a plus 2. So if I just bring down my other three terms, now we can combine some like terms. 21 plus 2 is 23, and 7i minus 6i is a positive 1i, or just plus I. So our final answer, 23 plus I. In the next example, you can do FOIL as well. If you prefer to write 3 minus 2i times 3 minus 2i and use FOIL, you certainly can. I'm going to use the pattern that is the square of a binomial. And what that pattern says we can do is when you square at a binomial, you're going to square the first term. 3 squared is 9. We're going to square the second term. Now when we square 2i, we want to make sure we square the 2 and the I. So 2 squared is 4, and I squared becomes I squared. And that is always going to be positive. And then there is a middle term. You're going to get 3 times 2i, which would be 6i, but we want to double that because we're going to get two middle terms. So the middle term becomes 12i, and it's a minus because we have minus between our two initial terms. So these are the same terms you would get if you were to FOIL. It just has the two middle terms already combined. Now we don't want to stop here because we have an I squared, and that needs to get replaced with a minus 1 times the 4 that was already there, makes this minus 4. So if I bring down my other two terms, now I can combine my 9 minus my 4, which is 5, and just bring down that minus 12i. Okay, on the next example, again, you can do FOIL, that's perfectly fine, but you should also recognize that these are the exact same two expressions, but they have opposite signs. Sometimes these are called conjugates. And so what we can use here is the difference of squares pattern. And this is just a pattern that helps us figure out what our answer is much more quickly than just using FOIL. And what the difference of squares pattern says is when you have conjugates like this, then your answer is just going to be the first term squared, so 7 squared is 49. The second term squared, 2i squared becomes 4i squared, and then it's the difference between those two. There's no middle term because if you were to FOIL this out, the two middle terms cancel each other out. One is positive and one is negative. So it's just the first term squared minus the second term squared. Again, you don't want to leave your answer like this because I squared needs to be reduced to a negative 1. And notice here that this 4 has a minus sign in front of it, so negative 4 times negative 1 becomes positive 4. So we actually end up with the sum of our two squares, which gives us 53. Okay, so we've done addition of complex numbers, we've done multiplication of complex numbers, now we're going to do division of complex numbers. And division of complex numbers really isn't anything other than rationalizing your denominator, which is something you would have done when you talked about square roots and cube roots. When we rationalize complex numbers, and remember, these are radicals because an I is a square root of a -1. So we do have a radical in the denominator, and we usually don't like to leave radicals in our denominator, so to undo that, we call it rationalizing. So to rationalize these, what you'll notice is that in this denominator here, we actually have two terms. So the only correct way to rationalize would be to use the conjugate. So what is the conjugate? Remember, the conjugate looks just like this term in the denominator, but with the opposite sign in between. So in this case, the conjugate would be 5 minus 2i. So what we're going to do is multiply the top by 5 minus 2i, multiply the bottom also by 5 minus 2i, so we're really multiplying the original fraction by just a fancy 1. I'm going to wrap all of these in parentheses to help remind me that I do need to be distributing here. So let's do the denominator first. When I see this denominator, because I'm using a conjugate, you will always have a difference of squares pattern in your denominator, just like the last example we did. So instead of foiling this all out, I know already what I'm going to get. I'm going to get the 5 squared, which is 25, minus the 2i squared, which becomes 4i squared. Now change that I squared to a -1. If I multiply that minus 4 times that -1, then this becomes 25 plus 4, or 29. So my new denominator is 29. Let's do the top. Now if you notice, you could distribute the 29 across. However, looking ahead a little bit, we knew that the denominator we got was 29 as well. So I am not going to bother distributing the 29. I'm going to leave it out front of my parentheses because we can then cancel out the 29 on top with the 29 on the bottom, and we get a reduced fraction, which is just 5 minus 2i. You always want to give reduced answers, so that's why you want to look for anything that you could factor out and cancel with your denominator. So this solution is just 5 minus 2i. Okay, let's try another one. On this next example, again, we're dividing two complex numbers, and the denominator has two terms in it with a plus sign in between. So what we want to do to simplify this is rationalize the denominator, get rid of the I that is in the denominator, and we have to use the conjugate to do that. So in this problem, the conjugate is going to be the exact same expression, but with the opposite sign. So we need a 7 minus 3i. So we're going to multiply by that on the top and also on the bottom. I'm going to wrap everything in parentheses so that I remember to distribute. So let's start with the denominator. The denominator will always be that difference of squares pattern because we're always taking a term times its conjugate. So the answer is going to be that first term squared, so 7 squared is 49, minus the second term squared. 3i squared becomes 9i squared. If we simplify that denominator a little bit, remember I squared becomes a minus 1, and a minus 1 times that -9 makes this become 49 plus 9, which is 58. So the new denominator becomes 58, and notice there's no more i's down there. That's exactly what we want to happen. We want to get rid of all of our i's in our denominator. So we've simplified the denominator. Now we need to simplify the top. And in this example, since we have -8 minus 2i times 7 minus 3i, the only way to simplify that is to FOIL it out. So -8 times 7 is -56. -8 times -3i is positive 24i. -2i times 7 is minus 14i. and negative 2i times negative 3i is positive 6i squared. Now remember that I squared turns into a minus 1. So that minus 1 times the 6 that we already had makes this become a minus 6. So we're going to have negative 56 plus 24i minus 14i minus 6. We just changed the sign in front of that 6. Now we do have a couple of like terms on top, so let's combine. Negative 56 minus 6 is negative 62, and 24i minus 14i is positive 10i, all over that 58. Now can I leave my answer like this? The answer is no, because all of these numbers, negative 62, 10, and 58, they are all even numbers, so that means they're all divisible by 2. So let's go ahead and divide everything by 2 so that we can get a reduced fraction. Negative 62 divided by 2 is negative 31. 10i divided by 2 becomes 5i, and 58 divided by 2 becomes 29. And here's our final reduced answer. Okay, in our last example with division, we have an expression that looks like this, and this doesn't look initially like a division problem, but what you need to recognize is that a negative exponent means flip over your fraction. So this means take a reciprocal. So 4 plus 3i raised to the negative 1 really means 1 over 4 plus 3i. And here we have an I in the denominator, which we don't want to have. So this is where we're going to need to use a conjugate, because we have two terms in our denominator. So the conjugate is going to be 4 minus 3i, and we're going to want to multiply by that on the top and also on the bottom. And I'm going to wrap everything in parentheses. So in the denominator, we're going to get that difference of squares pattern. 4 squared becomes 16, minus 3i quantity squared becomes 9i squared. Now I squared becomes a minus 1, which is going to change this sign out front. So this minus 9 out front is going to turn into a plus 9. And with that 16, that makes the new denominator 25. Let's see what the numerator is going to be. We just have on top 1 times 4 minus 3i. So that's going to stay 4 minus 3i. So here's your answer, 4 minus 3i all over 25. Just to mention, this is also the same as 4 over 25 minus 3i over 25. So you could separate this into two separate fractions if you wanted to as well. So just know that those are the same. Okay, so we've added and subtracted complex numbers, we've multiplied them, we've divided them. The last thing we're going to talk about is powers of I. So what we're going to notice is that there is a pattern that develops with the powers of I. So every power of I turns out to be the same as one of these 4 patterns that we're going to develop. So let's see how this is derived. We already know that I to the first is equal to the square root of negative 1. So we're just going to call I to the first I. So I to the first is just going to be the same as I. When we square both sides, we know that I squared turns into negative 1. So I squared is the same as negative 1. So here's the first 2 pieces that we have in our pattern. To figure out what I cubed is, what I'm going to do is I'm going to take the statement I squared equals negative 1, and I'm going to multiply the left side by I and also the right side by I. And the reason I do that is because I times I squared turns into I cubed, and negative 1 times I becomes minus I. So I cubed is going to be the same as minus I. Now to get I to the 4th, we're going to do that same thing again. I'm going to multiply both sides of this equation by I. So I'm going to multiply I cubed by I and also negative I by I. As long as I do it to both sides, I'm keeping the equation balanced. So I times I cubed becomes I to the 4th. Negative I times I becomes negative I squared. And remember what negative I squared turns into. I squared is negative 1. So this minus sign stays put, and I squared turns into negative 1, so a negative negative 1 turns into positive 1. So I to the fourth turns out to be positive 1. Now if we were to keep going here, let's take I times the left side and I times the right side of that last equation. I times I to the fourth is I to the fifth. 1 times I is I. And I was the top of my list right here. So I to the fifth is the same as I to the first. Okay, let's try it a couple more times. I'm going to multiply by I on the left side and on the right side. So I times I to the fifth becomes I to the sixth. I times I is I squared, and I squared is negative 1. So I to the sixth is the same as I squared, which was negative 1. Let's try it one more time. If I multiply it by I on the left side and on the right side, then I times I to the sixth becomes I to the seventh, and negative 1 times I is minus I. And that's exactly the same thing that I had for I cubed. So look and see what's happening. I to the first is I squared is negative 1, I cubed is negative I to the fourth is positive 1. I to the fifth takes us back to the top of the list and gives us back I to the sixth is the next one down, negative 1. I to the seventh is the next one down, negative I. So I to the eighth should be 1. I to the ninth gets me back to I to the 10th would be negative 1. I to the 11th would be negative I to the 12th would be back to 1 again. So we cycle through this pattern of 4 powers of I. So every power of I is one of these 4 values. You just have to figure out which one it is. So how do you do that? Well, if we take an example, I to the 26th, I'm going to show you the long way and then the short way. So the long way would be to take I to the 26th, and since this cycle up here is a cycle of length 4, I am going to break up the number 26 into 4s, as many 4s as I can. So for example, I to the 26th is I to the fourth, 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 and then an I squared. Why is that? Well, remember you add exponents. So I've got 6 4s here. So 6 times 4 is 24, plus 2 more gets me to 26. So all I did was break up 26 into powers of 4. Why did I do that? Well, each I to the 4, remember in our pattern over here, is the same as 1. So each of these I to the 4ths become a 1. So the only one that's left is the I squared. And what was I squared in my chart over here? I squared was negative 1. So this last I squared becomes negative 1. So when I multiply all of these together, what's my final answer? Negative 1. So I to the 26th is the same as I squared, which was negative 1. So that's the long way, to break up your power into powers of 4, and then you have a leftover power or your remainder power. The shortcut is to just do some division. Since our cycle is of length 4, we can take the power that we're given initially and divide it by that cycle of length 4. 4 goes into 26 6 times. 4 times 6 is 24, and the remainder that I'm going to get is the one that's important. I don't really care how many times 4 goes into 26. All I care about is the remainder, because that's the one that's going to determine my answer. So this remainder determines the fact that I to the 26th will be the same as I squared. And since I squared is negative 1, I to the 26th must be negative 1 as well. So let's practice that shortcut on this next example. If I have I to the 37 All I need to do is divide 4 into 37. Remember, my cycle is of length 4. 4 times 9 is 36, so I'm going to get a remainder of 1. I don't really care about the 9 up here. All I care about is the remainder is 1. What that means is that I to the 37 is the same as I to the 1, since that's what my remainder was. And I to the 1 is just I. It's going to stay I. So this answer must be I. Okay? On the next example, we're going to do kind of the same thing. However, we do have a negative exponent, so that kind of messes things up a little bit. So the first thing you want to do is get rid of your negative exponent, and remember that negative exponents take reciprocals. So I to the negative 17 is the same as 1 over I to the positive 17. Once you've made that exponent positive, then you can use your shortcut of dividing by 4. So let's divide 4 into positive 17. 4 times 4 is 16, so I'm going to get a remainder of 1. That means that I to the 17th is the same as I to the 1. And I to the 1 is just I. So I to the negative 17 is the same as 1 over I. Now, can I leave my answer like that? And the answer is no, because I is not allowed to be in your denominator. It's a radical, so we have to rationalize this. Now, when you rationalize a single term, you don't need to use a conjugate. So in this example, to rationalize I, all I have to do is multiply the top and the bottom by that same I. Let's see why this works. If I do that, then I times I gives me I squared, and I squared is just negative 1. So I've lost my I in the denominator, which is exactly what we wanted to do. We don't want I's downstairs. So all I had to do is multiply by I to make that happen. Now I'm also going to get something new in the top. Let's look back at our top. We're going to get 1 times I, which is just I. So if I simplify this just slightly, I divided by negative 1 is the same as negative I. So negative I is our final answer. So on these negative exponent powers, flip them over first so that you get a positive exponent. Then you can divide by 4, use the remainder to determine which power of I you're equivalent to. And if you have an I in your denominator still, you would want to rationalize. And in this case, we just had to rationalize by multiplying by I. And then simplify your final answer. Okay, we're going to do one last example. We want to figure out what I to the 8th minus I to the 7th is. So let's figure out what each of these two powers of I turn into. So let's start with I to the 8th. I'm going to take 8, divide it by 4. 4 times 2 is 8, and so the remainder is 0. So think about our pattern of 4 up here. We go back to our list. Which of these has a remainder of 0? It's got to be the multiples of 4. And you could see this in another way as well. If you just count, this is I to the 1st, I to the 2nd, I to the 3rd, I to the 4th. I to the 5th would be back up here. I to the 6th, I to the 7th, I to the 8th is right here. So any power that is a multiple of 4, just like I to the 8th is always going to be the same as 1. So I to the 8th is the same as I to the 4th, which was 1. So this becomes 1. Now let's figure out what I to the 7th is. So if we take 7 and we divide it by 4, 4 goes into 7 once, and the remainder is 3. So that means if I look back at my chart, I to the 3 is the same as negative I. So that means I to the 7th, the original problem, is the same as I to the 3rd, and since I to the 3rd is the same as negative I, this becomes a minus I, and then there was subtraction between these two answers. So 1 minus a negative I becomes a double negative, so this turns into 1 plus I. So our new answer, only has I to the first power in it. You never want to leave powers of I bigger than 1 in your final answer because it's not considered simplified. Every higher power of I is going to be reducible to one of these 4 possibilities. Okay, so now you should be able to add, subtract, multiply, divide, and find powers of I, all with complex numbers. This concludes our notes on complex numbers. Good luck.